Okay, so this video is 2 of 2 for B3, the Engineering Physics Fluid Dynamics section. Numbers 1 through 5 were on the first video, and so this video will be 6 through 6 through 8. So we have number 6, which is talking about a reservoir that's open to the atmosphere, and then there's an outlet pipe that leads down to a turbine, and the difference between the top of the reservoir and where the turbine is height h. First question A says, state the difference between laminar flow and turbulent flow. It doesn't say anything about calculating a Reynolds number. I don't know how you would calculate a Reynolds number because you don't have the information to solve for it. I'm looking up the Reynolds equation now. Yeah, that'd be speed times the radius times the density times the viscosity. I think that Reynolds number, if it's over 1,000, the flow is turbulent. But it just says, what's the difference between laminar flow and turbulent flow? And so the mark scheme kind of, says it well. It says in laminar flow, the velocity is constant. The velocity of the fluid is constant at any point in the fluid, but it's not constant for turbulent flow. And I think that's pretty good. It's like if looking at a streamline, if you have like a flow of liquid, if you have a flow, along a streamline, at any point in the streamline, all of the particles have a constant velocity, even if your streamline is curved. If you have a streamline, the velocity of the particles is tangent to the streamline and constant. Whereas turbulent flow is kind of all over the place. So that's the difference between laminar flow, and turbulent flow. All right. Then B says, show that the speed of water exiting, or when it gets down to the turbine, is radical 2gh using Bernoulli. So we have Bernoulli. It's the constant. It's 1/2 rho v squared plus rho g z. Z would be the height, plus the pressure is a constant. And so we have 1/2 rho v squared at the top plus rho gz at the top plus atmospheric pressure up at the top is equal to 1/2 rho v squared, let's say reservoir, maybe velocity of reservoir, and then velocity at turbine has two different velocities. And we have rho g z down at the bottom, and the turbine is open to atmospheric pressure, so it's P0 down at the bottom. All right, so right away we can get rid of the atmospheric pressure from both sides, and the density of the water is found everywhere on both sides of the expression, so we can get rid of that as well. We can consider that the reservoir is at height 0, so z is going to be 0 for the reservoir, so we can get rid of that part. And if the reservoir area is large, which it's a reservoir, so it is, especially large relative to the turbine pipe, the velocity there is 0. So we can get rid of that portion of the equation as well. Okay, so then we basically have nothing for the reservoir side. There's no speed there. We consider height 0 there, and atmospheric pressure cancels out both sides. So on the right side, we have 1/2 times the turbine speed squared plus g times z being h. And so I put the gh on the other side of the equation. Also got rid of the 1/2, and so I get turbine speed squared is 2gh, so square root both sides, and I get that the turbine speed of the water is radical 2gh, which agrees with the mark scheme over here. And and it says, do not accept simple use of v equals 2as. Basically because it says show using the Bernoulli equation. So you have to do it that way. All right, so that is B. All right. right? And then they give us a bunch of data. They give the density of the water, the viscosity of the water, the diameter of the outlet pipe, and the velocity of the water at the outlet pipe. And they want to know the Reynolds number for the water flow. I bet the follow-up is it turbulent? Yup, is it laminar or turbulent? Saw that coming. All right, so let's calculate the Reynolds number. Okay, Reynolds number. So R, Reynolds number, is velocity times radius times density. This is all of the fluid, radius of the pipe, speed and density of the fluid over the viscosity of the fluid. So we put the numbers in. And I don't even really know why I'm rewriting this because it's right here. Yeah, sometimes the mark scheme takes a little bit of a shortcut, but the numbers as described, the velocity, the radius of the pipe. Oh, I just remembered. It's not radius, it's diameter. In classic IB fashion, they use R and VR rho over the viscosity, where you might think that R would stand for radius. Oh, no, it's diameter. So yeah, R, this R right here is actually diameter. Great. Thanks, guys. Yeah, so I was about to say, it's like, hey, wait a minute. The radius is not 0.6 meters. The diameter is 0.6 meters. Right, the diameter is 0.6 meters. R in that expression is diameter, not radius. Yay! All right. So anyway, when you run the numbers through, we get an R number, a Reynolds number of 2.72 times 10 to the 7. Okay, actually, I'll give them this. It says, accept use of radius of 0.3 meters, giving a value of 1.36 times 10 to the 7. So I guess even if you did say, oh, R is radius, you still get a Reynolds number that is high. And you wind up with turbulence when your Reynolds number is greater than 1,000. So that is 10 million. So yeah, yeah, that's pretty turbulent. So on CII, is it reasonable to assume that the flow is laminar? No, it is not, because the R is way over 1,000. So it is not reasonable to assume laminar flow. And actually, it actually says in the problem, it's like, oh, assume that the outflow is laminar. I actually thought of that. I was like, we're talking about a reservoir and a turbine pipe, and they think that flow is going to be laminar? Heck no. It's definitely not. It's way not. So anyway, yeah, it's going to be turbulent when the water gushes out. So that is that. All right, that was number 6. Now let's look at 7, and we have another pitot tube. So to do number 7, first we have to realize that the pressure, one of the ways we can express pressure is rho gz. That's one of the reasons why in the Bernoulli expression we have pressure plus 1/2 rho v squared plus rho gz is equal to, is a constant, right? So you can only add those things together if they're the same. And so the deal with the pitot tube, if we just consider for a minute, because we have a difference in a height here, we have tube A is 0.1 meters and tube B is 0.32 meters. And so following that Bernoulli continuity, the 1/2 rho vx squared plus rho g zx, the 0.1 meters, is 1/2 rho vy squared plus rho g zy, the 0.32 meters. Now we know that at y, the velocity there is 0. That's the stagnation pipe. So the 1/2 rho vy squared goes away. And so basically it's asking, show that the velocity is about 2 meters per second. Yeah, so we're solving for the velocity at x. So there we go. We can get rid of the density. We don't need the density. It cancels out. And so in the end, the velocity at x is radical 2g zy minus zx, which is exactly what this is saying right here. 2 times 9.81 times 0.32 times 0.1, And what we wind up with is 2.08 meters per second, which is about 2 meters per second. And then it says the viscosity of water is 8.9 times 10 to the negative 4 pascal seconds. Estimate the Reynolds number for the fluid in your answer 2A. And remembering that in Reynolds number, R helpfully is diameter, not radius. But I'm not sure that matters much because, I mean, we're talking about like orders of magnitude on Reynolds number. So anyway, but we do know the diameter, it's 1/2 meter. And it's saying to estimate, so it says like viscosity of water is 8.9 times 10 to the negative 4. That's like 10 times 10 to the negative 4, which is really just like saying 1 times 10 to the negative 3. So I'm going to just say like 1e negative 3 for the viscosity. And 2 times 1/2 is, of course, a 1. So basically, the Reynolds number is going to be 1 times 10 to the 3 divided by 1 times 10 to the negative 3. And so the Reynolds number winds up being 1,000,000. Now, 1,000,000 is much bigger than 1,000, so I bet they're going to ask, is it turbulent? Yes, it is. And so let's go check the math. We said 1,000,000. Oh, they actually put real numbers in. See, this is the Bose-X. Like, what is happening here? They actually put the radius in. They use R as radius. And in the other problem, they use R as diameter. It's not going to matter because, like, you get in the right ballpark. It's interesting that they say estimate and they use the actual numbers. Whatever. So they got 6 times 10 to the 5. I got 1,000,000. But even so, by like the order of magnitude, it's way over 1,000. So we got our Reynolds number. That was a 1-point calculation anyway. And then it says, is your answer to A valid? Interesting. So A is valid. The validity, it says, assuming that the flow is laminar, right? But we just figured out that, no, it's not laminar. It's turbulent. So therefore, the answer to A, flow is not laminar, so the assumption is invalid. Interesting way of asking that question. And we have a Galileo thermometer. We saw that in class the other day. So let's see. Diameter shows a simplified model of a Galilean thermometer. The thermometer consists of a sealed glass cylinder, contains ethanol together with glass spheres. Spheres is filled with different volumes of colored water. Mass of the glass can be neglected, as well as any expansion of the glass through the temperature range experienced. Spheres have tags to identify the temperature. The mass of the tags can be neglected in the calculations. So it's really just like the weight of the water. It says each sphere has a radius of 3 centimeters, and the spheres, due to different volumes of water in them, are of varying densities. So they'll have the same size and the same volume, but the actual amount of water in them is different, so their densities are different. And then as the temperature of the ethanol changes, the individual spheres rise or fall depending on their densities compared with that of ethanol. So the buoyant force, the buoyant force is affected. And the graph shows the variation with temperature of the density of the ethanol. So the graph is over here. There's an indirect relationship. It says using the graph determine the buoyant force acting on a sphere when the ethanol is at 25 degrees Celsius. So using the graph following 25 degrees Celsius. And so at 25 degrees Celsius, the density of ethanol is 785 kilograms per cubic meter. It says determine the buoyant force. So we calculate buoyant force. Buoyant force is density of the fluid times the volume displaced times g. And so the volumes can be 4/3 pi r cubed. It said the radius of the spheres was 3 centimeters, I think. Yes, 3 centimeters. And so we have that volume, and we multiply it times the density of the ethanol at 25 degrees Celsius, which is 785 kilograms per cubic meter, times g, and we wind up with 0.87 newtons for a buoyant force. I don't need to rewrite it. It is right here in the mark scheme, but that's how they got it. A double I. Ethanol is at 25 degrees Celsius. That sphere is just at equilibrium, so it kind of hovers, neutral buoyancy. The sphere contains water of density 1080 kilograms per cubic meter. So basically at equilibrium, of course, we know that the net force is 0. So that means that the buoyant force upwards is equal to the weight going downwards. There's no drag force because the sphere isn't moving. It's in equilibrium. Or we actually don't know. We don't know if it's moving. I think we can assume that it's at rest, and that there's not significant drag there. So basically, it says percentage of sphere volume filled by the water. And so what they're getting at is that we can solve for the mass of the water, and if we know the density of the water, we can get the volume of the water. And so the buoyant force we figured out was 87 newtons. So 0.87 newtons is mg, g being 9.81, of course, and so the mass of the water, is about it's about 89 grams. And so knowing the density of the water is 1080 kilograms per cubic meter, we can solve for the volume. We get 8.21157, etc., times 10 to the negative 5 cubic meters, so kind of tiny. Now the full volume of the sphere, and so the sphere is 1.13097, etc., times 10 to the negative 4 cubic meters. And so figuring out the percentage there, I get 73%. Let's see what the mark scheme actually says. Hey, look at that, 73%. Go me. So that is correct. Dink. That is a terrible check mark. Dink. And it's a little bit better. Okay, last but not least, we have B. And B says room temperature slightly increases from 25 degrees Celsius, causing the buoyancy force to decrease. For this change in temperature, the ethanol density decreases from 785.2 kilograms per cubic meter to 785.16 kilograms per cubic meter. Average viscosity of ethanol over that range is 0.0011 Pascal seconds. Estimate the steady velocity at which the 25 degrees Celsius sphere falls. So we're going to use the, if it's moving now, so we're going to use the drag force. Okay, B. B is a little tricky in terms of how you approach it. Especially it says use of drag force to get 4/3 pi r cubed, which is volume. And so, so that's like the kind of buoyant force, that times 0.04, which is kind of like a mystery, which I'll get to, times G, equals drag force 6 pi times the viscosity times R times V, and you get 0.071 meters per second. The 0.04 is the difference in the density. And so, like before the temperature change, you had weight going down, of course, and you had buoyant force going up, and it was in equilibrium. It wasn't moving. There was no drag force. There's no mention of drag force. Then there was a temperature change causing a change in the buoyant force because there was a change in the density of the fluid, the density of the ethanol. The volume of the displaced fluid stays the same because the volume of the glass sphere stays the same. So that doesn't change, and G doesn't change. But since there was a change in the density of the ethanol, there's a change in the buoyant force. So that's what I wrote here. The change in the buoyant force is change in the density of the ethanol times the volume of the displaced fluid times G. And so that decrease in the buoyant force, so then it'd be like less upward force. So then there would be still the downward force of weight, and so the sphere would start to accelerate downwards. It'd be a net force downwards, but as soon as it starts to move, there's a drag on the sphere, which is the drag force. And then the drag force pops up, and the question said that the velocity was steady, which I assume is English for, Queen's English for constant. So steady velocity, so the sum of the forces is still 0, but the vertical forces are canceling. The decrease in buoyant force, that change in buoyant force, was balanced by the drag force that popped up, and so that's where they're getting, was I put in the change in density times the volume times g equals the drag force 6 pi viscosity, radius, velocity. And so that it's that change in the density, that's where the 0.04 is coming from. It's that density change there. That's where it's right there. And so I kind of stuck that in. Change in the density times 4/3 pi r cubed times g equals 6 pi viscosity rv. So if we solve for v by itself, we get that the speed is change in the density of the fluid times 4/3 pi r cubed g divided by 6 pi viscosity r. Did you get that? So put all the numbers in. I put the difference in the I keep on wanting to say viscosity. The difference in the density times 4/3 times pi times the cube of the radius, the 3 centimeters, put it in meters, and times g over 6 pi times the viscosity, which they gave us, 0.0011, times the radius again. And when you work it all out, voila, you get 0.071 meters per second, which agrees with the Mark scheme. And so that was interesting. And that was number 8. Those were all the recent B3 questions, and that's the end of video 2 of 2 for B3 paper 3 questions. Hope it was helpful. Thanks. Bye.